Good afternoon. All right, so last class we did Last class we did 8-39. So let's do a couple more examples today. We're going to do (8-60).
Excuse me, Professor. When is the homework due?
Okay, the homework.
Because it says it's due this Wednesday. Is that when our exam is?
No, our exam is, so I just put up the syllabus. So the homework is due on this Wednesday by 11:59 p.m. And then the exam is the next class day, which is Wednesday of the following week. And the reason, basically, and I've done this for all these, I've changed the homework to be due the review day. And that's so you get the homework done and then you review after that. So you can kind of try to get a big picture after it versus scrambling to get the homework done. I feel like a lot of people then don't get enough time to go back and review it. So you don't get the big picture. You're just scrambling to learn it versus you should learn it and then learn the review kind of puts the big pieces together. So that's why I'm doing basically the homework due on the review day, okay, or I should say by the end of the review day for all the exams. Okay. All right, so we're doing 8-60. Let's see. The adiabatic compressor of a refrigeration system compresses R134A from a saturated vapor at 160 kPa to 800 kPa and 50 degrees Celsius. What is the minimum power required by this compressor when its mass flow rate is 0.1 kilograms per second? Take the dead state temperature should be 25 degrees Celsius, and then they have a schematic for the system. So we have given, we have adiabatic compressor. It's got R134A. It has initially a quality of 1.0, so it's a saturated vapor. Then, and it's a pressure of 160 kPa at that inlet. Here the compressor compresses it to 800 kPa and a temperature of 50 degrees Celsius. They told us the mass flow rate is 0.1 kilograms per second. The dead state temperature is 25 degrees Celsius. And then they want us to find the minimum power required. All right, so then our schematic. The inlet of 1, where the volume shrinks down. We have our outlet. Got our input shaft there for power. It's adiabatic, so we got some insulation. That's a compressor. And any assumptions? All right. So where do we want to start? We're looking for that minimum power.
At state one.
So it's state one, but that's just the state. So what equations do you want to use to get there?
You want to find out what the work rev is.
The reversible work. Okay.
Reversible.
Yep. So that'll be our minimum work if we do this reversibly. Okay, so how do we get the reversible work? What equation do we use to get there?
We could use the Exergy balance.
Yeah, so Exergy balance. Open system. Okay. All right, so let's get that equation. All right, so we got our open system Exergy balance. How do we simplify this one? Neglect, X-destroyed, steady state, I see. So yeah, it's steady.
Adiabatic.
It's adiabatic, so that's 0. Okay, so we have steady state. The volume's not increasing or shrinking with respect to time. And then the other key one was we're making X destroyed 0 because we're looking for the reversible case, which is our best case because we're putting work in. So when we do this reversibly, it's going to be our minimum. Okay. If we were getting work out, that would be our maximum. Okay, so we're left with, and even then it doesn't, right here, for reversible, we can just change this whole thing to reversible. Apparently I'm shouting it, making it so big. All right. And we have mass flow rate at 1 carrying in flow exergy, mass flow rate at 2 carrying out flow exergy. So we have this. So what's our next step? Conservation of mass. Okay. And we have just one inlet and one outlet, so the mass flow rates are equal. So we have then mass flow rate, right? It was given to us, so then we can do our flow exergy here, right? That's what's unknown. So we have 1 minus 2. Neglecting kinetic and potential. So then we just have that. We put that, substitute that back in. We have our mass flow rate. We have our dead state temperature was given to us in the problem. So then we need enthalpies and entropies. So what do we do to get that?
Table.
Yeah, the table. So our states. So the states was mentioned earlier, and we could have started there. I just don't want you guys starting there and then starting to pull every information from the table off, because that you can get lost in just pulling a bunch of properties from the tables. So here we determined, you could just start with states at your first step, but just making sure your state is fixed and not starting to just pull properties. I would wait until you know what you need so you don't end up spending more time than you need to. So in our case, we have state 1, 160 kPa, quality of 1. So it's a sat vapor, so our state is fixed. Okay, so we can get any properties we need there. And then state 2, we have a pressure, and a temperature. And we'll end up seeing that's a superheated vapor, so our state is also fixed. All right, so now we can get enthalpy and entropy for each state. 241.14 kilojoules per kilogram. And then entropy, we have 0.9422 kilojoules per kilogram Kelvin. And then enthalpy, 286.71 kilojoules per kilogram for state 2. And then entropy for state 2, 0.9803 kilojoules per kilogram Kelvin. All right, so now we have our enthalpies and our entropies, so we can solve, and we get negative 3.42 kilowatts. So that's work in. So if we did this ran this compressor reversibly, it would only require 3.42 kilowatts of power input. Any questions?
Why don't you consider the T naught times S gen? Is this just because it's an open system? Like, what does that even mean?
Why didn't I consider that? Well, in this case, we were just looking Oh, and X destroyed was 0 for this minimum. So that's
That's
reversible.
right. Yeah. You're
So
right.
that's the T naught S gen term. So that would be 0 for the reversible case. But you could solve it that way. And that's what I'm about to mention. I'm not going to go through all the solving, but there are also 3 different ways, as I mentioned last class, to solve for this problem. Okay, so we know that X destroyed, and that would be the actual case, X destroyed, rate of Exergy destruction, is T naught S gen, which is for a work producing device is reversible out minus work useful out, or work consuming device is work useful in minus work reversible in. And we were looking for that minimum because we're a work consuming device. So we had this bottom one, and we were looking right for this value, right? So that's the Exergy balance where X destroyed is equal to 0, the rate of Exergy destruction 0, and you solve for work reversible, okay? And that's what we did. We did that, we went straight in. How do we know if it's work in, not work out? Well, with this one, the device tells us, I mean, it's a compressor, so you're putting a couple ways. You're putting work in to raise the energy, like the energy are inside each of the fluids. So at state 1, you have low pressure. State 2, you have high pressure, higher temperature. You're going to increase the energy inside that state. What those properties are. The other way to know is when we solved, we got this negative. When we solved the reversible, that negative told it was work in, right? Because right up here with this negative here, and then it's still there, that's assuming that if we got a positive value out of when we solved it down below, that we would have got that would have been a workout. By solving it, and it solved, and we came up with the opposite, then we got work in. We got the opposite of what we assumed. So it's a work in this example. Okay, work consuming. Okay, so we did this method right here straight for reversible work in. Okay, well, you can also go the route of solving for work useful, which is, the COE, and one of these 2 values. Right, if you take work useful and subtract off X destroyed, you get the reversible work, right? So we would have X destroyed would be from the Exergy balance, but because this would be the actual case, not the minimum. Okay, so that would have X destroyed there, okay, in the Exergy balance. We would leave that quantity in. We would put the actual work in for the work. And then this T naught S gen is our entropy balance. And we could go that route and put those 2, we could put this and this together, right? Or this one and this one together to get our work reversible, or solve for work reversible directly. And that's the quickest method. The one that we did is solving for work reversible that directly for this one, because that's all the problem asked for. Okay. If we were looking for X destroyed for the actual case, not the minimum or then going straight to the entropy balance would be the quickest, right? But we wanted work reversible. Questions on that? All right, next thing we could do for this problem is our second law efficiency, okay? So the second law efficiency is Exergy recovered over Exergy expended, which is 1 minus Exergy destroyed over Exergy expended. Okay. How would we figure out what's expended and what's recovered and what's destroyed?
Exergy destroyed is the reversible work. Well, actually, it's these formulas you put above. That'll be Exergy destroyed. The expended, I don't know anything about that.
Yeah. Yeah.
Is that the useful word?
Which one?
The expended?
Let's take a step back, and because we're trying to paint the picture in here of what's recovered, expended, destroyed. Destroyed's the easy one, right? It's what's recovered and what's expended. All right, so let's basically start with the Exergy balance, open system, but in this case, we're going to do the actual case, right? We did the reversible case to solve for this problem, right? Because they were just looking for the minimum work. So if we look at the actual, and simplify it, again, steady state. We still have X destroyed being left in there because it's the actual case. Volume's not increasing or decreasing, it's adiabatic. All right, so we got the actual work there. Put in our COE. And now we have 3 sections in this one. We got this, and this, right? And I'll take the easy one. This X destroyed is the destroyed, right? So now these other 2 sections, one's Exergy expended and one's Exergy recovered. Okay. So which is it?
Goes expended and then recovered.
So which one's expended, which one's recovered?
Work and then the mass flow rate is recovered.
So you're saying mass flow rate's recovered, this one, the flow, Exergy, and work is the expended?
Unless I'm wrong.
Then you'll say the opposite. No, it's correct. This is the work is expended, okay, or kind of the supplied, because you're putting work in, okay? And this is recovered because you're raising from the inlet to the outlet, the flow Exergy at the exit is going to be higher than the flow Exergy at the inlet, right? The work potential of the outlet fluid is going to be higher than the work potential at the inlet. So you're recovering Exergy. You're putting Exergy in, expending, or supplying it by that work, by compressing the fluid, putting that work in, and the fluid itself is recovering some of that. And not all that Exergy ends up going into the outlet. So some of that work potential gets destroyed, and that's how you define which is which, okay?
I think I remember seeing something like this where it was like, you know, I think it was something like heat plus work plus or minus destroyed. It was something very similar.
I mean,
Isn't that-
somewhere, it depends upon what device you have, so what's going on, because you could have heat be expended or recovered, you could have work be expended or recovered, you could have the change in flow exergy be expended or recovered. It depends upon the device. In this case, because we're putting work in, that's the supplied or expended, right? Because if you think about this, you have this negative sign here, and then we have negative that we end up getting for our work, right? So then it ends up being a positive, okay? Recovered, you're gonna have the outlet flow exergy being higher than the inlet, so you're gonna get a negative here, okay? So that tells you expended, recovered, and then destroyed is your difference.
I see, I see. Thank you for clearing that up.
Yeah. And that's how you can do it for any device, not even just the ones that give you different equations for. So if we put this together, we have expended, the bottom. So we have our actual work, right? Or that could be called the work useful, okay? And then we have the recovered. On the numerator, right? We can also look at this whole thing on the numerator is the same thing of what we got way up here. Right here for work reversible. So we could simplify it and say it's work reversible divided by work useful, okay? Is our second law of efficiency. You could also use the 1 minus and do the version 1 minus exergy stored over exergy expended, which then you just put in the 1 minus x destroyed or T naught S gen, and then have your work useful. Okay. Any questions? All right, let's do 8-90. All right, so given, let's see what we got. We got R134A is converted from a saturated liquid to a saturated vapor in a closed system using a reversible constant pressure process by transferring heat from a heat reservoir at 6 degrees Celsius. From a second law point of view, is it more effective to do this phase change at 100 kPa or 180 kPa? Take the dead state temperature to be 25 degrees Celsius and the dead state pressure to be 100 kPa. And then they give the schematic. Okay, so we're given R134A is our fluid. We have quality of 1. All right, so it's quality of 0 at state 1. So it's a sat liquid. And then it goes to a sat vapor, so saturated vapor. So we're at state 2, we have a quality of 1. The pressure change is 0. We have heat transfer, so heat is occurring at a temperature of the reservoir equal to 6 degrees Celsius, which is 279 Kelvin. The dead state temperature is 25 degrees Celsius. The dead state pressure is 100 kPa. Want us to find from a second law point of view, is it more effective to do this phase change at 100 kPa or 180 kPa? So second law. Great. All right. So second law, more effective at 100 kPa or 180 kPa. All right, so our schematic. We have R134A inside here. There's some heat transfer going on. We've got our boundary. Okay. So we're looking for the second law. From a second law point of view, what's more effective? And they have two different pressure choices, okay, for this process. So what do they think we're asking for here? When they're saying second law more effective, what do we think that might mean? What variable are we trying to solve for?
So if it's second energy, we need work reversible and work useful.
So looking at the two works for effectiveness, that might work. I think they're going about it, and I think that ends up working. No pun intended, but what they're really getting at with the second law and effective, without saying it directly, is they're looking for the second law efficiency, right? Because you think of a first law, how effective something is, that's a efficiency from just energies, thermal efficiency, COP. When they're talking about it from a second law, they're saying second law and effectiveness. They're trying to get at, they're getting at that second law efficiency, which will come down to the works in this case. But so our second law efficiency, I'm just gonna write it again. Because we need to figure out exergy recovered divided by exergy expended, 1 minus exergy destroyed over exergy expended. Okay. All right. So we need to figure out what's recovered and what's expended and what's destroyed. Where do we go for that again? Our exergy balance. Okay, so in this case, though, we're doing a closed system, right? All right, so we have Exergy bounds, closed system. What can we, do we have dots on this? It shouldn't be there. All right, that's why I was looking at it weird. All right, so we have, do we have heat transfer?
Yes.
Yeah, so, oh, I messed up in another place. I'm mixing up my Exergy balances, sorry. So there's, all right, let me just stop for a second, make sure I don't have any other mess ups. Okay, so we have heat transfer. Okay, so we got to leave that in, right? So we got 1 minus T naught, and then we have the reservoir temperature, TR, that was given. Okay. Do we have work?
Probably not, no work. Well, maybe from the actual weight on top of the.
Okay, so we need to determine whether we do or not. I forgot the right assumptions here.
If there's a change in volume, we will have boundary work.
If there's a change in volume, we won't have boundary work, correct. So is there a change in volume in this case?
I'm gonna say no because pressure is constant.
All right, so let's do this. Let's do a little PV diagram. Oh, wrong way. All right, so we have our constant temperature lines. Okay. Where's state 1?
Is on the left side. It's a saturated liquid.
Yeah, so where's state 2?
On the right side.
All right, keeping pressure constant. All right, so if we do that, we have a change in volume. Okay. So we have, so that means we have a change in volume, so we have
So
boundary
there's
work.
boundary work, yeah.
Yeah. All right, so the other key thing is you can't keep, if you keep delta P0 and delta V0, you're at the same point. There's no process, okay? For one thing to be held constant, the other independent intensive property has to vary, okay? If those are two independent, like if we did specific volume, let's say, those are two independent intensive properties. So if there's no change in either of them, you're at a single point, right? So we're at just 0.1 if there's no change in volume, no change in pressure. So if volume's constant, pressure has to change. If pressure's constant, specific volume has to change, okay? That's the other key thing of it. All right, so that means we do have boundary work. Okay, then this is the dead state pressure. This basically right here on the right side side here is the work being done on the surroundings. And since we have boundary work, this piston's moving. We said the volume's increasing, so this piston's going to move up, right? Are we doing work on the surroundings then? Are we having to push the surroundings?
Yeah.
Yeah, okay, so we have that term. We can't cancel it off. We have a change in volume, we have that, okay. And we have X destroyed. And then we have mass and our times our change in exergy per unit mass, our non-flow exergy, okay? All right, so we have these terms. I'm gonna move the non-flow, this non-flow exergy in to the left side, just so everything's to the left of the equal sign, and I'll get to that why in a second. Okay, I'm gonna erase this. All right, so now we have it look like this, okay? So again, I'm gonna take the easy one. Here's destroyed. For our exergy. Now we got to figure out what's expended or recovered. And everything here in this brackets, that's work useful, okay? All right, so we need to figure out is that the exergy by heat transfer expended or recovered, this work useful, and we got to figure out this change in non-flow exergy. Okay, so we got 3 things, but only 2 things to go for. So that means 2 things are going to be in the same thing. So going by kind of what we looked at in the last problem of how to determine what's expended or recovered, what do we think this heat transfer is? Is it expended or recovered? Expended, okay.
It's heat out, so is that expended?
It's heat in, so that's expended. So it's transferring heat from a heat reservoir. So and we're putting heat in. You can also think about it from that PV diagram that I erased. Let's sleep it up here so I don't have to erase it. Right, to make work out, we have to put in to get some work out, we have to put a heat in, okay? The other way is to do a TS diagram, and you'll see it's heat in also. Okay, so that means we have heat in, so that would have a plus sign on heat transfer, which everything here then is positive. So that means this ends up giving us a plus sign, which is expended / supplied, okay? All right, how about this work useful? Is it gonna be expended or recovered? Is it work in or work out? Okay, we got recovered. Okay, someone said, yeah, so you're gonna have it be recovered. Okay, because it's the boundary work itself is going to be a positive value in here. Okay, and then that's the negative on the whole thing. So you're gonna end up getting a negative there. Okay. Now we have the last is 1 minus 2 of the non-flow exergy. Is it going to be expended or recovered? It ends up being expended. Okay. All right. Why? The other, and I think that's what I should have done on this one, is I shouldn't have brought it over the left side. That's why I messed up on that one. If this is, it's easier to see from there. This ends up being a positive. Okay, so it's going to be expended. All right, so now we have the, let's put it back. Okay, so we have recovered, work useful, and then we have one minus T naught TR heat transfer plus this. Okay. So then we have work recovered. We have our heat transfer expended and our non-flow exergy change expended. Okay. All right. So in this part, when we're looking at this question, we can figure out what we have and what we don't have. We don't have, we haven't solved for work useful yet. We have T naught, we have TR, heat transfer, mass, and then we need to get properties. First thing I'm going to start off with is, does this mass help us with determining whether something is effective or not? Can we do something with this mass?
If
They
we
didn't-
could
yeah.
divide it out, but why
Yeah,
would you want to?
Yeah, so we divide it out because the mass is really just a scalar in a closed system, right? State 1 and state 2 stay the same. You're just making the piston cylinder device bigger or smaller. You're just looking for effectiveness. The mass just scales the system, doesn't change the efficiency. Okay. All right. So we divide it out and we just get lowercase. All right. All right. So now we got to figure out work useful, heat transfer, and then our change in non-flow exergy. Okay. So work useful, lowercase, is our boundary work minus the work on the surroundings, lowercase. How do we figure out the boundary work?
It's at a constant pressure. You could use the formula from state one. It's like in a row,
Yeah, so
row
actually let me write.
pressure times changing
That's right.
volume.
Yep, so let's write boundary work first. All right, so that for lowercase would be change in specific volume versus change. If it was uppercase work, we would have change in volume. Okay, so pressure is constant for our system, so we can get P, pull pressure out of the integral, we get P V2 minus V1. Okay, so if we look at work useful, we have P, change in volume, and then work surrounding is then just the dead state pressure and change in volume. Okay. So we have our dead state pressure, and then for this pressure, we're going to choose the, we'll do the 100 kPa first. Okay, so then we have our pressure. So how do we get the change in volume?
Table.
At the table, yeah.
Yeah, so tables, so we have state 1 is 0 quality and pressure is 100 kPa. State 2 is 1 on the quality and the pressure is the same. Okay, so the nice thing about this, because it's going from quality of 0 to 1, we can use the FG values. So if we are looking for V2 minus V1, that is the same in this problem as VG minus VS. Okay, which we get 0.19182 meters cubed per kilogram. All right, so that means we have the work and work on the surroundings we can solve for, okay, and get the work useful. So if we do this for the work part, that's just P delta V, we get, for the boundary work, we get 19.18 kilojoules per kilogram. For the useful work, we get a whopping 0 kilojoules per kilogram. Okay, because this pressure and this pressure are 100 kPa. Pressure inside the cylinder and the pressure on the surrounding pressure are 100 kPa. Delta V is the same. So all the work we're doing inside the cylinder is offsetted by just pushing the surroundings. So the useful work or the work potential is 0 then. the exergy associated with that boundary work is 0. Okay. All right, so that gets us a whopping 0 kilojoules per kilogram. Okay. So we can already know this is not very effective and move on to the 180 kPa, but I'm going to go through the whole problem and still solve the second law. Because if we go here, we're looking for this. What's our second law of efficiency going to be for this 180 kPa?
0, because it's work useful
0.
all divided by anything.
Yeah, so we already know it's 0, but I'm still going to go through the process of getting these other quantities, okay? All right, so we have left is the expended, which is the 1 minus T naught over T R times Q plus our change in non-flow exergy, right? So how do we get, we have our temperatures, so that means we need to get the heat transfer per unit mass and then our change in non-flow exergy. How do we get the heat transfer?
It's given.
It wasn't, no, it said there's heat transfer, but the value wasn't given. So how do we get the value for heat transfer?
Conservation of energy.
Yeah, so our COE. Closed system. Neglecting kinetic and potential energy. And then dividing by mass. We have this, right? We have already solved for the work and there's only boundary work. Okay, so we already have that. That means to get heat transfer, we just need U1 and U2, right? Well, U1 minus U2 is UG minus UF, which is UFG, okay? So we can get at 100 kPa, UFG is 198.01 kilojoules per kilogram. 0.01, okay. All right, so then.
Quick question. So let's say the boundary work that we got was work in, so it was negative. Would we plug in a negative value for the boundary work, or?
In here, yes.
Yeah.
Yeah. Yeah, this is just, so this one right here, why isn't my green working here? All right, let's go with orange. Nope. All right, so that, okay, that sign, now it decides to work on. All right, so that sign right there is telling us that if we solved here and we got a positive out of our boundary work equation, so then we just put in, this has a negative, and then that's the positive goes in right there, okay? If you had work in, you would put the negative inside that. So this is just from this one's just from the setup of the equation, and then I like to do a parentheses for your value substituted in, okay?
Thank you.
All right, so now we have basically U2 minus U1. We didn't have to get individual ones. We have UFG. So we get heat equal to 217 0.19. Kilojoules per kilogram. And that's heat in. Okay, ends up being positive. All right, so we have then that. Then we just need the change in flow or non-flow exergy. Okay, and I don't have this solved individually, but we already have U1 minus U2, which is negative UFG. We have V1 minus V2, which is negative VFG. We just need negative SFG. We get 0.88008 kilojoules per kilogram K. All right, so if we put then, I don't have the individual what this ends up being, but I have the 1 minus T naught over TR times Q plus the non-flow exergy. We get 30.28 kilojoules per kilogram. All right, so our second law efficiency is 0 kilojoules per kilogram divided by 30.28 kilojoules per kilogram. Okay, so 0%, right? So the next part is we have pressure of 180 kPa. Okay. Do our equations change at all for that? Like we went through here. Do the equations change?
No, just the numbers.
Yeah, now we just gotta go through the process of getting a new state value when it's 180 kPa and getting those values. All right, so we would have a new UFG somewhere. $188.20, a new VG minus VF, our VFG is our 0.10974 meters cubed. Per kilogram, and then SFG at 180 kPa is 0.79848 kilojoules per kilogram Kelvin. All right, so now we just start going through and solving stuff. Okay, so our new boundary work, PDV, so we get 19.75 kilojoules per kilogram, if we subtract off the work on the surroundings, so we have work boundary minus the work being done on the surroundings, which is this part, right? We get 8.779 kilojoules per kilogram. And then from our COE, we can get our heat transfer of 207.95 kilojoules per kilogram. And then last is our Exergy expended. So going through and getting our non-flow Exergy, solving and putting it with our Exergy expended from the, or Exergy from the heat transfer, we get 24.61 kilojoules per kilogram. So then our second law efficiency is 8.779 kilojoules per kilogram divided by that 24.61 kilojoules per kilogram. We get 0.3567 or 35.7%. So then we know this one's more effective, right? So in this case, it was a little easier to, as mentioned earlier about just looking at works. You could have looked at work usefuls, right? But it's not always that easy, because if it wasn't zero, like them having zero and then a positive number made it easier. But the you can see the work expended changes, because we had 30.28 here, and then we had 24.61 here. So there's also the role of the expended changing too. So you got to be careful. So some of them, it might not be so easy to see which one's better than looking at the second law. All right, any questions? First time seeing a question. I'm not sure of that question, first times. Okay.
I have a quick question.
Yeah.
The change in Exergy, how do we know that it was not zero? Like, usually we assume steady state. I know that makes it.
Well, this is a closed system. So when it's a closed system and we're putting in heat, right? So then the energy and Exergy inside our system over here is going to change. Okay, there's no steady state like that. Same with over here. The energy inside our system changes because we're putting in heat, right? It's not, if this was a closed system, let's say we had a fixed volume system and we were putting in, or it's your house or something like that, and we were putting in a rate of heat transfer. and there was some rate of heat transfer leaving. Now that you could say is steady state, right? It would be, you could look at it in a closed system one or open system and then just cancel off the mass flow rates because you're dealing with rates. Now that's where you can bring in that steady state assumption or not.
So
Okay.
if like the boundary was insulated, is that also like another point we can neglect it?
What, neglect
Change-
what?
The change in exergy?
No, so no, that you cannot neglect that term ever when it's in closed system like that, unless it's kind of rate based. Okay, this change in exergy is what's going on inside your system. So anything on the external does not matter from it. Okay, that is what's going on inside here. Okay, is this change in exergy. So that's what's going on inside our system. What's crossing our system or changing on the outside is these terms here. Okay, so this on the right doesn't matter what's going on the left. Okay.
I think I understand a little bit more now.
Yeah, if it was a rate-based problem, open system problem, now you're looking at how it's changing with respect to time. Okay, and if it's staying the same with respect to time, then that's where we have our steady state assumption. And this, it's not, it's changing. We're just looking at like, let's say it right now at this instance, and then state 2 is an hour from now or something like that. So it's the change over that. It's just that change from state 1 to state 2. Okay. All right, so another question is, what's expended or recovered? Okay, and that's looking at positives and negatives. So here we have heat transfer is in, right? Even when we solved it down below, so we saw heat transfers in. So that's a positive. So that's going to be expended, okay? We had work boundaries, so we have this negative from this term right here, but then we have, when we solve for the boundary work, it was a positive, right? So we end up with a negative, so that's going to be recovered, all right? And then here we have the change, and we're going to have positive here, so that's going to be our expended also, okay? And then the other one, we did that same thing from the identifying it from for the compressor, right? So this is a rate-based one. When we did our Exergy balance, we looked at what's expended, what's recovered, right? We end up having this negative right here, right? But then we it ends up being a negative work because it's work in. So the negative times the negative gives us this overall is a positive, okay? And then this we have a positive on this side right here, but this ends up being negative. The flow exergy at the exit is more than the inlet. So we have a negative, so we're going to get negative here, okay? And then this one's the difference. So what doesn't, so expended minus our recovered, so we're going to get, that's going to be destroyed, okay? All right, any other questions? Greta?
I had a question on one of the homework problems, if you want to go over that.
Okay. I mean, I got a quick minute or not, but we're over time here, but.
It was, all right, give me 1 second. was question 38, 838. It's an ideal gas, and I was just confused on if the volume is constant or not, because you can use the ideal gas law to figure out that it's not constant. I just don't know how to get the U value or the internal energy value or the entropy value.
Well,
Because
it's
it's an
not a
ideal gas.
constant volume because you're compressing it. So it's
Right.
volume's changing. So now,
And how do I figure out the change in energy and internal energy?
all right, so it's an ideal gas. So then you have ideal gas equations, internal energy, you have CV delta T.
Exactly. But it's not a constant volume though.
It doesn't matter.
Oh, you can always use it.
Yes, delta U is CV delta T. Doesn't matter now. Yeah.
Oh, okay. Thank you.
That's just how you get CV. That's just how they derive CV, okay, when they do the experiment. But in chapter 3, we determined that for a ideal gas, delta U is only CV delta T.
Okay. All right. Thank you. That helps me a lot.
Yeah, just like delta H is always CP delta T. It doesn't matter if it's constant pressure or not anymore. Okay, that's just how they get the CV and CP value.
So, maybe this is just a little off, but so then that number you get is not necessarily like very accurate, is it? It's
What do you
more of
mean?
like so because you're assuming that it's a constant.
No, it doesn't matter anymore. So you have to go back to chapter 3. It doesn't matter. We're not assuming it's constant volume or constant pressure. Delta U is CV delta T. It doesn't matter where you got CV anymore. Okay.
Okay.
CV's formal definition is like the partial of the partial of U with respect to temperature keeping volume constant, and CP is a partial of enthalpy with respect to temperature keeping pressure constant. Well, for an ideal gas, they determined, and that's the Joule experiment, determined that we can just make that for an ideal gas, it's only a function of temperature. So that means there's no partial anymore. So then CV equals du dt and CP equals dH dt. Okay, so
that makes a lot more sense now. I
so
see.
it don't matter anymore how they get this. Okay, that's just the equation now, right? When we have du, we can put that in. When we have dH, we can put that in. Okay.
Yeah, thank you.
Yep. All right. You guys have a good rest of your day, and I'll see you on Wednesday.